going to start with a little brief kind of history. We'll talk about how expectations and changes, basically expectations of people have of their homes have changed the way that we build our houses today. We'll talk about the sound building science principles from control and predictability to what is the building thermal envelope and these control layers that we talk about, and kind of being precise about the language that we're utilizing out there in the field when we're talking about houses. So to jump in, this house here is 116 years old, and I often ask that question, why? Why is it 100 years? Why is it over 100 years old? Again, if anybody wants to unmute and interact, you're more than willing to do that. But the basic reason it is because it's so inefficient. It's uncomfortable in a lot of ways. This happens to be my own house, and I've done a lot of work on it, so it's no longer inefficient and uncomfortable or whatnot. But it does bring up this other kind of side of it, is that I'm scared to death every time I do something to this house. This house has tremendous drying potential, and that's the primary reason why it is a 100-year-old house. But it's fundamentally, these older houses fundamentally really epitomize this idea of applied building science, because if you don't apply that building science correctly on these types of houses, you could have this house fail in a matter of weeks, years, or months there, depending on what. And we don't have that same opportunity cost, I guess, that we have in new construction to plan and really understand how we're putting things together and applying the building science. In this case, we're doing something to the house, like adding insulation. In this case, I decided to add insulation on the inside of the house because the brick is unpainted brick. And if I did it the other way, most likely that I would create a situation where that brick would fail, because I'd be trapping the ability for that moisture to move. If that brick was painted on the outside, that painted brick would probably start spalling and the paint would start peeling when I insulated it on the inside, because I do have only one means for this assembly to dry, and that is to the outside in that case. But I've got to take those things into account. This porch, you can see in the front, I totally rebuilt, and I created an unconditioned or a conditioned crawl space underneath it. And if you look really closely here, you'll see some moisture staining in these locations here. And that's a consequence of changing the dynamics of how this house functions and whatnot. So we need to understand these things as we move forward here. Another interesting thing about older houses and kind of the history and introduction of applied building science is, when did we actually start insulating our houses? Does anybody have an idea?
Put newspaper on the walls in the 1890s.
Yeah, in this kind of
I don't know
ways.
if that's insulation, but
Yeah, these are types of older insulations that were in our houses. We really, we did do that in some cases, especially up in climate zones 6 and 7 in the mountains and whatnot. But really, it wasn't until the 1960s, mid 60s, early 70s, when it became kind of more of the norm to insulate our new houses there. But as you point out there, in the early 1920s, 1930s, we were starting to get houses that were insulated. And in a lot of cases, those insulated houses that were wood framed houses and wood sided houses and painted houses, the paint started to peel in those houses there. So in 1938, this guy, Tyler Rogers, wrote this article titled "Preventing Condensation in Insulated Structures." And he made this hypothesis that the peeling of paint was caused by indoor relative humidity inside the houses. And he made this big, bold proposal that we needed to control that indoor relative humidity and how it's moving, and that we needed to install interior vapor retarders, and we needed to ventilate our attic spaces there. And by the 1940s, that actually became one of the first things that got codified in construction in the early versions of what we now call the IRC there. Now, that was a great hypothesis, but he really had no science or anything to really justify that conclusion there. And along comes this guy named Bill Rose, who's a forensic research architect. He's since retired, but he used to work at the University of Illinois in Urbana-Champaign. And he basically looked at the research or the ideas that Rogers put out there and basically came to the conclusion that Rogers jumped to this kind of prescriptive solution without really fully understanding everything that was happening in that houses there. He didn't take into account the idea of the temperature of the wood siding and the whole idea of condensation and how condensation happens. He didn't take into account that siding isn't a material, regardless of the cladding material that we decide to use, it's not going to stop all of the moisture from bypassing it and getting further and deeper into the assemblies. He basically didn't look at the house as an integrated system and how this system and the synergies of the different materials that we put together create performance or degradation in the assemblies that we put together there. So what we see that, these things have been codified into the codes in the past, and we're still working towards trying to understand the ramifications of those things that were codified in the code, like vapor retarders. And we have kind of this myopic view of vapor transport only being stopped by or only being managed by vapor retarders. And we'll see later in this presentation and also in our more modern codes that we're starting to understand how much moisture moves with air, and that air leakage and getting control and predictability of air flow is equally as important, maybe even more important than what a vapor retarder is trying to do in our wall assemblies there. So another thing that we should need to think about in kind of introducing the idea of applying building science is how long we actually live in our homes. What do you think? What range here makes sense to you? Or have you guys heard about there?
I was here 5 to 7, but I think 10 to 15 is more reasonable.
Yeah, it turns out that the National Home Builders Association did a study back in 2018, and they came to the conclusion that on average it's in that 13-year range there. And in today's world, it's probably even longer than that because of the COVID era interest rates that people got and people not willing or wanting to move because of the economics of the situations that are out there now. But we see that people are staying in their houses for long periods of time. Me in particular, I've been in my house almost 30 years here. So I think there are a lot of people out there like that as well. Regardless, however, though, for the majority of people out there, it is the largest purchase that they've ever made with the least amount of knowledge about the product that they actually bought and also how to utilize or maintain that product that they're living in there. With that said, they also have tons of expectations about how their house should perform and what their house should be able to do for them. This is an example of what's happening in my neighborhoods in Northwest Denver. I am on the Front Range here. We're seeing a lot of these older houses built in the early 1900s scraped, and new houses being built or new ADUs being built next door to them. And it really kind of brings out this idea of how modern day expectations have changed the way that we build our houses to meet those modern day expectations. If we take comfort as an example of that, in 1910, does anybody have an idea of what they think people's idea of comfort of that house or their expectation of that house would be?
Couldn't have been much.
Yeah, maybe just getting out of the elements, just getting out of the rain. But even if it was that level of comfort as just staying dry and warm, they were actually willing to interact with that house, weren't they? they were willing to put on a sweater in the wintertime. They were willing to shovel some coal or put a log on the fire to keep warm in that house versus our modern day houses where we are basically wanting to walk around in our underwear from room to room and floor to floor and be quote unquote comfortable in that house. And when that fundamental comfort expectation isn't met by a new house, we end up getting into lawsuits or arguments or warranty issues or other things that we don't. But we see that this change in expectations from being able to live in a house and understand that it's not going to provide all of the comfort for me, and therefore I'm going to wear a sweater in the wintertime when I'm inside that house, to today where I don't want to wear a sweater. We've changed the way that we've built these houses in order to meet this level of comfort. We've added complex heating and cooling systems. We've added insulation. We've tightened up the building envelope, let alone all the electronics and everything else that have been added to our houses, window technologies, and so forth and so on. So we've built these houses. We've stick built for quite some time, since the early mid 1800s here. But the other thing that's changed is not only that we're adding insulation and tightening up the building envelope, but the number of people involved in the construction process has changed pretty dramatically. In the past, we had these houses built either by a construction company that had a crew that took it literally from foundation through finished carpentry, or a bunch of people that came together to help build that house from foundation through finished carpentry, to today's world where we have subcontractors come in, and we have, on average, according to the National Home Builders Association, 300 people touching the house, 300 individuals touching the house, divided into little subcategories that we call our trade partners now. We have a subcategory for electrical, for insulation, for framing, for concrete work, all these different things that people are coming in, and very few people that when we call ourselves builders, very few of us really understand building a house from foundation through finished carpentry. We have that skill set of either running a schedule or doing electrical or doing drywall or doing one of these subsections of this process here, which means that we need to think about, again, how we're putting the house together in this different way from a new lens. And the applied science lens is that, because ultimately I think our goal is similar to what John Ruskin put out there years ago. There's a building science educator named Mark LaLiberte that often uses this quote, and I'll let you read the quote here. But ultimately, we're trying to put something forward that lasts over time, that we're going to be proud of, and that we want to be able to pass on to our descendants ultimately out there. And we want to be able to do that in whatever climate zone we actually live in and build in. In Colorado, we happen to live in the most diverse climate zone state in the country. We have everything from climate zone 4 to climate zone 8 here. We're also in a very forgiving part of the country in the essence that we're live in the dry climate zones. So climate zone 6 or climate zone 5, for example, crosses the country, but the different parts of the country have different moisture loads, and we need to understand what we might have to do differently, or we need to understand that if we make mistakes, those mistakes might show up in Colorado after a number of years, where in Pennsylvania they might show up after a week to a few months, just because of the difference in the moisture loads of the exterior macro climate that we live in there. We also have these things called microclimates inside of our houses that we have basically across the country. And what would be an example of a microclimate inside our houses? Anybody? Things like bathrooms, kitchens, laundries, crawl spaces, attics, where we have severe differences really in humidity and temperature and those types of things inside of our houses. So we live in this dry climate zone, which kind of governs the direction of moisture flow most of the time of the year, meaning that moisture always moves from higher concentrations to lower concentrations. And that's why they ultimately say, let's put the vapor retarder in the warm and winter side of the assembly, because the moisture drive in Colorado, we generally have more moisture inside our houses than outside our houses. So the moisture drive is from more to less to create that equilibrium across the assembly there. We also want to remember that energy moves from high to low, or from higher concentrations to lower concentrations. Pressure drive is from high to low as well here. So when we're starting to apply these ideas in these different climate zones, and specifically in climate zone 6 and 7, where you guys are, we think about the building science, and ultimately what we're trying to do is gain control and predictability of airflow, heat flow, and moisture flow inside of those assemblies, because those are the drivers that are going to ultimately create problems for us. What the biggest problem that we see are moisture related problems, and heat, air, and moisture itself are those things that accentuate moisture that creates the problems in our houses. So if we can gain control and predictability of these things, we can make sure, or better ensure, that our houses are going to have that long-term durability that we want, and are going to be able to meet those core expectations that our clients ultimately have here. So building and science, is kind of incorporating all of these things, from architecture to plumbing to acoustics to enclosures to mechanical systems and whatnot. But what we see also from this fundamental idea of building science is that the synergies of these things come together to achieve that thing, that additional thing that it couldn't achieve on its own, which is, I think you can think of it as the overall performance of the house, or you can think of it as the um, two things coming together to achieve something that they couldn't achieve before. That's the fundamental definition of synergy here, where we have an air barrier system and a thermal barrier system coming together to create our building thermal envelope that gives us this third thing, this control and predictability of airflow, thermal flow, and moisture flow. Or we have a duct and a fan coming together to be able to get us better control of moisture, give us better indoor air quality, be able to heat and cool these houses. But they couldn't do them in just by themselves. They need that synergy of these things coming together here. So again, kind of that overarching building science principle that we're trying to hammer home here is this idea of control and predictability, control of airflow, thermal flow, or heat flow, moisture flow in those houses. We use these different control layers to start gaining that control there. But it's not just really control that we're ultimately wanting to get. We're also wanting to get predictability of the flow of these things around our houses and in our houses. And I put up McDonald's here because we want that level of predictability. I don't think there is a McDonald's in Salida, but if you go to McDonald's in Colorado Springs or Denver or New York or Paris and you order a Big Mac, you know exactly what you're going to get. You know exactly what you're going to feel like after you eat it. This is the idea of predictability, that we just know what we're going to get if we can control the environment that those things are being made in there. Because ultimately, from a house perspective, all of these things are trying to create a balance, an equilibrium across the building thermal envelope. And when we get to the building thermal envelope, we can see that that defining boundary is ultimately so important in our houses because of the equilibrium, the drive of moisture across the assembly, for example, to create equilibrium on each side. And if we can understand which direction the drive is happening on the majority of the time, we can gain more predictability of that moisture flow or that heat flow or that air flow through the house there. So I prepped you to grab a piece of paper. If anybody has a piece of paper, you can follow along with me. But the first thing we want to do with this piece of paper is we want to fold it like is described here. And what we're ultimately doing is creating a roof, right? Is this roof easy or difficult to build? Ultimately, it's a rhetorical question. It's pretty easy to build. Now, I want you to take that roof and I want you to crumble it up and I want you to put it back into this assembly. This is what we're actually trying to build out there. Rather than that simple structure, you're trying to build that out there, right? So we have these two houses here. We have the house on the right that is going to perform. The snow's going to come off that roof easily. We're going to be able to protect the walls and windows pretty well with a decent overhang. Then we try to build this architectural, whatever, I don't know, monstrosity or whatever you want to call it, on the left here. And it's not only super difficult to build, but think of the snow loads and and what's going to trap the moisture on that house. How's it going to drain? How's it going to function as a roof assembly there? So when we're talking about building science, we're also talking about understanding the simplicity of things. And if we're going to ultimately make it more and more complex, what are we going to have to do in addition to it to make sure that we're going to have an assembly that works and works well? What is an overhang ultimately meant to do? Whoops. Shade those windows and structure, protect the walls from water intrusion and whatnot. We have the wall assembly itself. What is it meant to do? Define the conditioned space, define that building thermal envelope, maintain that conditioned space on the inside of the home. And then we have windows that are supposed to provide natural light, connection to the outside, views. We want to take those into account. But there's also downsides to all these things as well. Windows, for example, if we have excessive window to wall ratio, we're going to have an assembly that is significantly weaker from the perspective of energy than it is than it would be if we had less windows in that assembly there, for example. So design really matters. And design matters not only from the perspective of the aesthetics, but from the perspective of the performance and what we're trying to get out of that assembly there as well. And that performance is often secondary, I think, from the aesthetic side of the equation. And the idea here is that building is a team sport, and we need to take all of these things into account when we're building this house. And we need to act more from the perspective of it being a team sport than from the perspective of one professional really drives the process here. And we kind of really learned this idea or came back to this idea after the Marshall Fire, because the Marshall Fire incentives were so keen on creating a house that was performing, that was potentially electrified, that was energy efficient. And these thousands and thousands of dollars were spent to incentivize a certain level of construction. But when only one portion of the team was trying to execute that for the homeowner, they weren't always successful in being able to do that. So we really understand that each professional plays a role in this design and construction process. They have to understand from the beginning, is there a goal? It can be a pretty simple goal to meet code compliance, or it can be a comfort goal, it can be a performance goal, or all those types of things. And then ultimately, what's being designed, can it actually be built there? What construction materials and practices are the teams able to use? Are they willing to use? Have they used in the past? Can they serve the same purposes as what might be designed and called out for on the architectural set there? Who's responsible for what? what teams are understanding the code requirements and what aren't, and should everybody understand that? And does everybody understand the idea of synergy, building science, all these things that we're talking about, which ultimately takes us to this idea of the design charrette and team kickoff meeting, to be able to focus the team's work to get input from each of the team members in the process of how this house is going to be designed and built there, so that the architect isn't putting something out there that really isn't appropriate for the climate or the region that it's being built in, and or isn't, the trade partners don't have any understanding or haven't worked with materials that have been designed out there. Understanding the people's expectations and goals, the construction design and strategies, gathering the input from the key contractors, and potentially the authority having jurisdiction as well here. So design integration process helps us from understanding opportunity costs, but also constraints. And one of the things that I'll just go back to real quick was that idea of window to wall ratios and windows, and what we're doing there. If we put constraints on the design team and the execution team to understand that every window in that house needs to be designed and planned for from the perspective of aesthetics, from the perspective of capturing views, from the perspective of energy loss, from the perspective of how difficult it is to make it an airtight and weather resistant opening in the home. All of these things need to be thought of, and the only way that they get thought of is by bringing everybody into the construction design process there, so that we can have a house that will actually work and perform there. So my idea here is that construction's a team sport. Performance is the goal of that sport, and building science are basically the rules of the sport. And everybody understanding those things will help us move forward there in unison, so that we can meet the overarching goals of the house, which means that we might have to put some constraints on engineers, on architects, and on builders, saying that we're going to use this new material, or we're going to have to justify every single opening, or we're going to have to figure out how to design for the code requirement that says that every header is supposed to be an insulated header. Well, we aren't asking the engineers to actually do that, but we're going to get performance benefit if we follow the code's advice and requirement to actually do that. Now, taking that into the code and what the code is saying, the first thing that we want to understand from a code perspective is the definition of the building thermal envelope. What you see from this definition of the building thermal envelope is that it's basically an assembly of things that are coming together to create this clear and defined boundary condition between conditioned space and exempt or unconditioned space. So from that space inside the house to that space outside the house. This clear boundary condition is often defined by these things that we call control layers. And there are a number of different control layers that we're talking about that create the building thermal envelope. We have exterior sheathing, that is an air control layer. We have water control layers with our cladding systems and our weather resistant barriers. We have interior drywall that can also be an air control layer, combined with vapor control layers and thermal control layers. And I like to add this additional one, what I call the thermal condensation control layer, which might be continuous insulation on the outside of our assemblies there. Now, all of these different control layers, it become rather confusing because some of these control layers can serve multiple purposes. Some of these control layers are potentially redundant, but make the building better. And from a code perspective, we're often talking about the idea of belts and suspenders. Now, recently, somebody pointed out that everybody might not understand the idea of belts and suspenders. So I guess I'm going to explain it a little bit. When the guy wears a belt to keep his pants up, but he also is wearing suspenders because maybe the belt malfunctions or something. What we have that redundancy. I have two systems. I'm wearing two systems to ensure that my pants stay up here. That's the idea of belts and suspenders here. So from a code perspective, belts and suspenders can easily be explained by the idea that we have exterior continuous exterior sheathing on the outside, and we have continuous interior drywall on the inside. They both can be a primary air barrier system and or a supplemental air barrier system, depending on the type of insulation that we're using. What we know is that by having both on the house, we're going to have a really tight, well-performing envelope there. But what it makes us also think about is that we really should think about which one is our primary air barrier and which one is going to be our supplemental air barrier there to make it even better. Which one's going to be the belt and which one is going to be the suspenders in this certain equation here. And we'll come back to that in just a minute. Before we go into that, I wanted to talk about design a little bit more and talk about this idea of form factor. The form factor is the ratio of its exterior surface area of the building or that building thermal envelope to its interior floor area. This is created by this ratio. And ultimately, what we see is that the compactness of the simple cube is the most efficient way to build our houses, but it's often not the most aesthetically pleasing for the people that we're building for there. So when we start adding in dormers and bump outs in our building structure, we're adding additional surface area to the structure, and we need to take that into account during the design process to be able to ensure that we're going to be building a house that actually performs. From an energy efficiency perspective, less building thermal envelope surface areas fundamentally means more energy efficiency, more performance, more comfort in that house, less operational costs there. Now, when you take it down to kind of these types of diagrams, you can see that the building thermal envelope on the right of this single-story building built on a slab is defined here. That's what the code is trying to do, is get you to determine what is the surface area of this building thermal envelope, what are the assemblies that are separating conditioned space from unconditioned space. Now, apartment buildings limit that exposed thermal envelope or exposed surface area to the exterior, but when we have a single family home that's a cube might have the same floor area as a single family home that has this big interior, in essence, courtyard like symbol C here or figure C here. They have the same floor area, but they have significantly different surface area, and therefore they have different heat loss as well and different performance of that building envelope there. So again, going back to the design process there, we need to think about the consequences of the bump outs, of the dormers, of the different things that might look architecturally pleasing there, but also ultimately might be detrimental from a performance perspective or from a warranty perspective or from a water management perspective. And those types of things. And does it really make sense? Is it worthwhile to do that, to add that dormer to the assembly or not? And there are lots of reasons why you might want to do it, and those reasons could outweigh, I guess, the performance reasons. But right now, we're not kind of balancing our decision-making process. We're pretty much just focusing on the aesthetics right now, instead of having a balanced decision-making process there that takes everybody into account from the building team as well here. Now, when we're talking about the building thermal envelope and we're talking about really all of these control layers, we're talking about the need for continuity and them being continuous all the way around the building envelope. And this idea of continuity comes up a lot in construction. We think about continuity as being this unbroken whole or without interruption. And the first place that we start thinking about the idea of continuity is the continuous load path from our roof all the way down to our soil. Now, we want to broaden that understanding of continuity and take it into the idea of needing a continuous air barrier all the way around our house, a continuous thermal barrier all the way around our house, and a continuous building thermal envelope that includes our water resistant barrier all the way around the house there. And again, the control layers ultimately help us gain this continuity there. So continuity is a fundamental feature of codes. Codes are asking us to build this building thermal envelope that has continuity on all 6 sides of the assembly that we're building. That house, if you just take it into its simplest form, is a 6-sided box. And the continuity needs to go around all 6 sides of the box to ensure that we have control and predictability of airflow, moisture flow, thermal flow, but also bulk water and other things like that. And the ultimate why is because of this. Moisture is the thing that destroys houses. It's the number one thing that's going to create building durability issues in our assemblies. We know that things get wet. We know that we need to let them dry. We know that they get wet from the start, from the outside, from the inside, from the start, and that we have repeated wetting problems in our houses, not just from a plumbing leak, but from maybe snow melting off our roof, or from those periodic rainstorms. Every time it storms outside, we get water that bypasses a window flashing that had a small issue in it or something like that. We also know that moisture flow transport mechanisms are not always following gravity. Gravity is 90% of it, but we have capillary action, which means that moisture can move actually up. It's like moisture moving up in a tree from the soil up to the leaves. It can defy gravity, moisture can. It moves by diffusion and it moves with vapor, and we have condensation, and then we have solar drive there. In Colorado Springs, it's a big stucco market. Stucco is an example of a hygroscopic, a material that absorbs moisture. And in our late afternoon storms in the summertime, you can severely get a moisture load in that stucco. Then the sun comes up and drives that moisture into the assembly by heating up that stucco and that moisture on the south side of the assembly there. So we have all of these things that can happen. And ultimately, what we're trying to get is this hygrothermal balance in our houses, where our wetting mechanisms equal our drying mechanisms. My house, that 116-year-old house, before I did some building science things to make it more comfortable and whatnot, ultimately had that hydrothermal balance. Whenever it got wet, it had the ability to dry. It had the ability to dry because energy was moving in from the inside to the outside pretty freely because there's really no insulation in the house. It had the ability to dry because air was moving freely from inside the outside or outside the inside to dry out those assemblies. So I have heat source to get evaporation. I have air to get evaporation. I have all these drying potentials in that house. And that's why I'm scared every time I do something to my house to make it more comfortable or more energy efficient or better from an operational cost perspective, because I've changed the drying potential of that house. And I need to think about the drying potential of that house. I know it's going to get wet from bulk water, from capillary action, from air transport and vapor diffusion. I need to understand how I'm going to let it dry now that I've changed its drying potential. And that's why I didn't insulate from the outside, for example. I know that its drying potential is from inside to outside through that unpainted brick. Now I need to think about that when I'm building a modern day house. These modern day houses now, in the figure on the top right hand corner, maybe that's a 2x6 wall or a 2x4 wall. I have a certain X amount of heating load in that house to make it comfortable in the winter time. That heat is trying to always escape the house. And some of that heat is moving through that assembly and moving to the outside, as represented by the light pink arrow. If I'm building a passive house, on the other hand, I still have that same load. I have some type of load on the inside of the house, but less of it's getting to the outside. And therefore, that heat that was normally drawing moisture that might be on the exterior sheathing is not getting there anymore. That surface is getting colder and colder. So the codes right now are saying, let's rely on the vapor retarder. Let's go to the IRC section R702.7 vapor retarders and understand what we can do. Well, I need to understand the building science because the code doesn't say automatically slap on a class 1 vapor retarder, some 6 mil poly in that wall assembly there. It says you have a variety of choices. You have a choice to not have any drying potential to the inside by putting 6 mil poly on the inside, or you have a choice of promoting drying potential from the inside to the inside by just using drywall with latex paint on it. And now you have an assembly that is more forgiving, more has greater drying potential. And I have to say, well, is my drying potential equal to the outside as it is to the inside or not? And I need to think about those things there. But ultimately, if we keep in the back of our mind that we want to build drying mechanisms into our new houses versus wetting mechanisms, we want to prevent the house from getting wet, but we know we're not always going to be able to do that. So we need to promote those drying mechanisms. Otherwise, moisture is going to get in those walls. And you'll see here in this example, it's moisture by the process of diffusion, moisture moving directly through the pores, the microscopic pores of the drywall into that assembly, and then ultimately hitting that cold surface of the exterior sheathing and condensing and creating that bulk water. If I can keep moisture in its vapor state, then it has the ability to dry at some point. And by drying, I mean it has the ability to diffuse in the opposite direction, to diffuse or dry back into the house there, rather than staying in that assembly. Once it changes state and moves into its liquid state, it's almost impossible to get it to dry. And that's why we end up getting mold growth and those types of things happening in our assemblies. And even though we're in a dry climate, we have lots of instances of mold in our houses because we aren't protecting them from this potential here. Now, the picture on the right is similar to this picture in that it's defining moisture diffusion. And what we know is that more moisture moves with air than it possibly does by diffusion over the course of a heating season or a winter in our homes. The moisture drive is from higher concentration to lower concentrations. So we know that we have more moisture in the wintertime inside our house than we have outside our house. So the moisture drive is from inside to outside through the drywall into that assembly. If I put a vapor retarder in that assembly, I am, for most part, stopping that moisture diffusion from getting further into the assembly. But when I put an outlet or any other type of penetration in that wall, I am getting air leakage into that assembly, and I'm going to get more moisture than could ever diffuse in that or through that drywall. And it's about tenfold more moisture. It's an extreme amount of moisture that can move with air versus the pathway of diffusion there. So, ultimately, if I have 35% relative humidity in air that's 70 degrees, which is pretty much what I want in the wintertime in our houses, I want that 70-degree air for comfort. I want 35% relative humidity for comfort so I don't get the nosebleed and whatnot. If it hits a surface that's at 40 degrees, it's going to hit that dew point, which means that it's going to change state from its vapor state to its liquid state. That 40 degrees is easily achieved at that exterior sheathing there in our modern day well-insulated wall systems there. So we want to control that flow of moisture in there. If we don't control the moisture and it does condense and we put a class 1 vapor retarder on it, it doesn't have the ability to dry back out. If I can keep it in its vapor state for longer periods of time, I can then allow it to dry back out, because the code says if I put that continuous sheathing on the outside, I've moved the that 40 degrees is here now versus out here with my continuous insulation, and therefore is not going to condense. And I'm also allowed to use latex paint on my drywall, and it's ultimately going to be able to diffuse or dry to the inside of this assembly here. Versus this case where my 70-degree air at 35% relative humidity, it's going to hit that dew point, some point inside the assembly here. It's unlikely that it's going to actually condense when it's inside the insulation, but when it hits that first, what we call the first condensing surface, or a hard surface that it can condense on, it's going to create that liquid moisture there. And again, once it's hit its liquid state, it's not going to dry out there ultimately. So design and build with that drying potential in mind. In this case, we're seeing that we have drying potential to the inside of the assembly by the process of evaporation and diffusion, and we have drying potential to the outside of the assembly with ventilation and a clearly defined drainage gap here. What we see is that drainage gap is super important. And in Colorado, we tend not to take advantage of that drainage gap. It's called a vented rain screen here. And in your climates, you're definitely within the WUI zones and whatnot, and with the new WUI codes that are coming out, we have to always remember that these spaces need to be properly screened to ensure that we're not allowing fire embers to get into the space, but also allowing moisture to free drain out of that space. We need about a 3/8 inch gap in order for a water droplet to drain freely down through the space and then ultimately out of the assembly here. You can use furring strips, you can use other manufactured designs in order to do that, but ultimately we're relying on gravity to work, and gravity works. We know that moisture is going to bypass whatever type of cladding system that we're going to put on the home, and we need to direct that moisture down and out and away from our foundations there. We have that weather resistant barrier along our house or on the house. We put a vented rain screen on so that we have a net free area where moisture can flow down, but then we're also adding ventilation there, basically from stack effect, which just means what happens to air as it warms. It naturally rises. So air is going in at the bottom of the vented rain screen and going up and out. And that ventilation behind there promotes evaporation. And we're going to get that continuing drying of the assembly. And as a byproduct, we get longer lasting siding. We get paint jobs that last for longer periods of time. And we get assemblies that don't get wet, or if they do get wet, they have additional drying potential so that we don't get molds or whatnot. The other types of moisture we need to think about is capillary action. And another thing that we don't do a lot in Colorado is we don't put capillary breaks in our assemblies. In this case, we see that moisture is moving upward in this foundation wall because there's no capillary break between the footing and the foundation wall itself here. Unfortunately, sill seal is a misnomer. It's not designed to actually seal that junction between the sill plate and the foundation. Its primary role is actually to be a capillary break. It might as supplementary be a air sealing, but it actually doesn't work very well as an air sealing because our foundation walls aren't completely level and smooth and flat, and we might have to shim it to make it square and level there. So we need to actually install these capillary breaks in these different locations and ensure that they're installed well and not just hanging and flapping in the wind for capillary action. And then in this case, in the middle case here, we need to do other things in order to make it an airtight assembly, which is basically seal this joint between the sill plate and the foundation. And that's what the code specifically calls out for in the air barrier, air sealing, and insulation installation table, is that we need to seal separately that joint between the sill plate and the foundation. And then in the IRC, that's where it calls out for this capillary break between the foundation and the sill plate here. When we're building with these different materials, understanding the permeability or the ability of moisture to move through the material becomes super important there. So if you think of a Gore-Tex jacket, for example, when I'm exercising with a Gore-Tex jacket on, I'm sweating on the inside of that jacket, creating moisture on the inside of that jacket, and that fabric has permeability to allow moisture to move through it from the higher concentration next to my body to the ambient air around me outside. That's what permeability is the ability of moisture to move through the material from one side to the other side there. And when we're building these assemblies, we could do what's called a vapor profile map to determine where is the most impermeable piece of the assembly. In this case, latex paint has 5 perms, drywall 40 perms. Look, closed cell spray foam only has 1 perm. Where's the closed cell spray foam? It's to the outside of the assembly. I also have OSB that has 2 perms, which is to the outside of the assembly. I also have asphalt roofing material that has less than 1 perm, and it's to the outside of the assembly. So if I didn't know better, and I also put a class 1 poly in this assembly at this location on the inside, I'm going to, in essence, be trapping moisture in that assembly there. I always want to have at least one side of the assembly having drying potential there. So this idea of vapor profiling mapping helps us understand where I'm going to get that drying potential, how I'm going to build in that drying potential into the assembly. I can still do this vented or unvented raftered assembly. I can still use spray foam, but I need to make sure that I don't have, in essence, a vapor retarder on both sides of the assembly that will ultimately trap that moisture. Because more and more moisture moves with air, then by the process of diffusion, this is diffusion on this side, this is air leakage on this side, it's very, very difficult to stop both of those things in a roof assembly because you have that air that's carrying moisture right up against that assembly to the outside. So diffusion is going to happen. And then we want to put our can lights and we want to put our outlets and we want to put other things in that assembly as well. That makes it difficult. So how do we get control and predictability? One of the big things is by sealing up the holes and stopping that airflow through the holes. What we need in order for air or moisture to move through holes is we need 2 things. We need the hole itself, and we need a pressure across that hole to push or pull air through the hole. If we don't have both of those things, then air will not move. So think of this, the rubber membrane of this balloon is the building thermal envelope. So think of it as the building thermal envelope. We have equalized pressure on each side of that building thermal envelope or that rubber membrane. Because this balloon is tied off here, if I untie the string, then the balloon shoots across the room because all the air is being pushed out of it. I have more pressure on the outside of the balloon than I have on the inside of the balloon, and therefore air is going to go out the hole. If I tie this off, I no longer have a hole, and the pressure is going to be equal. So I need two things to happen in order for air to move across the hole. I need a driving force, which is a pressure difference across the hole, and I actually need the hole. Now, which is easier as a builder to take advantage of or to control? Is it easier to control the hole or the pressure difference across the hole?
The whole,
Definitely the hole. And the code, the air sealing, the air barrier, and the insulation installation table helps us understand those holes that we should be specifically looking at. But the code also tells us that we have to seal every single hole. And so really looking at that as an example of the holes that we should be looking for is our ultimate thing. What we know also with air is that air in equals air out. So if I define the building thermal envelope with the blue line around the building there, we are also defining a specific volume of air in cubic feet of air in cubic feet of air, basically inside the blue lines there. If I have a hole and a cubic foot of air leaves the house, then a cubic foot of air has to come back in the house. So air in equals air out, and air out equals air in. This is the fundamental principle of a blower door test. When I depressurize the house, I'm sucking air out of the house and I'm pulling air in through holes in the building envelope. There's a constant volume of air, but I can measure that air exchange as it's happening there with the blower door test. Now, when we have air coming in and out of our houses, we have the hole, but we also need driving forces or pressure differences across that hole. And that happens generally by these three mechanisms. The first is called stack effect, which is just described as what happens to air as it warms. As air warms, it rises, right? As air rises, it hits this top plane of the house and it seeks a hole. If it leaves on the high side, then I have a positive pressure on the high side pushing the air out or sucking the air out, and I have a negative pressure on the low side, which is sucking the air back in. So air out equals air in. With wind, on the windy day, on the windward side of the house, I have a positive pressure. On the leeward side of the house, I have a negative pressure. So air is being pushed into the house and air is being sucked out of the house. This is what's so detrimental in fire season on a fire day that was super windy, like what happened in the Marshall Fire. That negative pressure on this side of the house happened in the roof assemblies and in the wall assembly. So fire embers came over the house and were sucked into the house. And the fire started in the communities by burning the houses from inside out. And then ultimately, radiant energy started jumping that house fire further deeper into the communities from house to house that way. And then we have mechanical systems. Mechanical systems like our forced air systems or our bath fans create negative pressures or positive pressures around our houses. A bath fan is a simple example. I'm sucking air out and hopefully moisture out from my bathroom when I'm taking a shower to the outside. But if I'm sucking air out of the house, air has to come back into the house as well. I can have a forced air furnace in my house with unbalanced supply and return, so I can create unbalanced pressures as well inside my house. One example of this is a vented crawl space. So a vented crawl space, we think that we assume this ventilation air is going to go in one vent and out the other vent and pick up moisture and pollutants as it moves. The reality, however, is that the building thermal envelope at this plane separating the vented crawl space from the conditioned space of the house is not airtight. I have plumbing, I have electrical, I have HVAC, I have all these different holes in that assembly there that are very difficult to make airtight. So if it's 0 degrees outside, what do you think the temperature of the air inside the crawl space is? It's not 0 is the ultimate thing. And because it's warmer than the outside air, it means that this air is going to warm by stack effect and ultimately migrate up into the house, warm even more, migrate to the high side of the assembly, migrate out, air out equals air in. And we have this total continual process of air in equals air out in this loop that happens with ventilated crawl spaces in our assemblies. And that's why the code is really allowing and encouraging conditioned crawl space designs in our houses there. The code also further defines the air barrier. So we defined the thermal building envelope before, but the air barrier restricts and prevents the passage of air through the building thermal envelope. So one of the things that comprises the building thermal envelope is the air barrier system, or the air barrier control layer that is part of the building thermal envelope. And the code continues to define this notion of continuous air barrier, or the continuity of the building thermal barrier of these assemblies that go through the building thermal envelope. So the code itself wouldn't define one primary air barrier on the outside of our house or on the inside of the house. The code is saying that the air barrier is an integral part of the building thermal envelope, and that it's constituted by the continuity of our exterior sheathing as our primary air barrier on the outside, and our continuity of our drywall on the inside of the assembly, especially when we're using fibrous insulation like fiberglass in our assemblies, because we also have to enclose that insulation to get that stagnant pocket of air in those assemblies there. So this is why the code requires us to define the building thermal envelope on our construction documents. By defining the building thermal envelope, this boundary between conditioned space and unconditioned space, I can define how I'm going to get that continuity throughout the building thermal envelope. So I might turn in a drawing like this to the code official that says my primary building thermal envelope is on my primary air barrier within my building thermal envelope is on the outside of the assembly there. Or I might do it in this way that says that my whole building thermal envelope with the continuity of the exterior and interior air barrier systems is what I'm trying to achieve in this case here. But this also gives us an idea of understanding where the key leakage happens through the air barrier systems in our homes. It happens where different assemblies connect together, where the roof connects to the wall, where the walls connect with windows, where the walls connect with foundations. All of these connection points are the primary areas of where air leakage is happening in these assemblies. And that's why I often say that spray foam insulation is not the panacea that's going to solve all our problems here. Spray foam can be a great insulation material. It can help make the house more airtight in this assembly of things that we're talking about as that constitute our air barrier systems within our building thermal envelope. But spray foam is installed within the cavity of the wall assembly, and we still have those connection points that are leaky. So I do lots of blower door testing, and I've tested houses that are very tight with spray foam, and I've tested houses that are very leaky with spray foam. The issue is the installation and the attention to detail to ensure that we're getting that airtight house. So what I generally recommend is define your primary air barrier. It can be on the inside of the house with this Siga membrane, for example, or the continuity of your drywall, if you want to do an airtight drywall approach, or it can be on the outside of my house with this other Siga membrane on the outside, or zip systems on the outside as well. Is a WRB, or like a Tyvek weather resistant barrier, is it also an air barrier? Any thoughts? The reality is that it's not often an air barrier. It can be an air barrier. It's a great supplemental air barrier, but 99% of the time, it's not installed properly to actually be your primary air barrier. So it would be another of your supplemental air barriers. So if I put my primary air barrier here or here, and I also had a Tyvek type house wrap on it, I would have my primary air barrier would be my zip sheathing, or in this case, my sheathing. And then my supplemental air barrier would be my weather resistant barrier and my drywall. In this case, wherever I define my air barrier, the other side of the assembly is only going to help me make it a more airtight house, help me gain more control and predictability if I'm able to make that assembly work or work not. So this is why the code really looks at this idea of belts and suspenders to make sure that we have the belts and suspenders to ensure that we get the airtight house, at least as tight as the code is wanting us to do, which is 3 air changes per hour, or tighter if we can there. And these things need to be detailed out on our construction documents so that not only does the design team understand what the goal is, but the construction team can look at the details and understand what the goal of that project ultimately is here. So in this case, we've got
We have a
SIGA.
question.
Sure.
Can we pause for a question real quick?
So
Yes, please.
I think I understand the theory of multiple vapor barriers being a problem.
Okay.
Is
Wait,
there any
I'm sorry.
concern?
I've got to stop you there. Think of the language that you just used. Said multiple vapor barriers.
Multiple vapor barriers, like
Okay,
a vapor barrier.
we're not talking
Pardon?
about vapor barriers here.
No, I'm just trying to relate it to the same sort of thing. My question is multiple air barriers. If I have a tape zip, and in my case, it's typically an R6 zip on the outside of a house, and then closed cell spray foam sprayed on the stud side of that zip. So I've got multiple air barriers right there.
Yeah.
And then a Sega on the inside of the wall. Do I have any concern of multiple layers of air barriers in an assembly?
No. You
Okay.
might have concerns about multiple vapor retarders because some of those materials are both air barriers and vapor barriers.
Right.
But from an air barrier side, you don't. And in your case, I don't think you have an issue with multiple vapor retarders as well, because the SIGA is a smart membrane that will allow any moisture buildup in its vapor state inside the assembly to dry to the inside through it. It's kind of like that Gore-Tex jacket.
Okay. Yep.
Yeah.
Thank you.
Yep. So it's confusing in the code world because it calls out for your air barrier, but it also calls out for a lot of areas where the continuity of the interior air barrier is not maintained. For example, behind a tub on an exterior wall or on the attic side of a knee wall, those type of locations. It's calling out specifically for an air barrier. Well, if I put my primary air barrier on the outside, and the code also requires me to put an air barrier behind a tub on the inside, why is that? And that's this case of understanding the notion of the supplemental air barrier. The supplemental air barrier is primarily needed for air permeable insulation or insulation. All insulations, their job is to trap a pocket of air. It's the pocket of air, in essence, that creates the R value, and the density of the material, the more dense the material, the greater its ability to trap that pocket of air and get a higher R value. So spray foam traps lots of tiny pockets of air, and therefore its R value is so much higher than a fiberglass bat or blown cellulose. But the difference between spray foam and these air permeable materials that are shown on the screen here is that spray foam blown at its proper thickness is also an air barrier. These materials are not an air barrier, so you have to put the supplemental air barrier to enclose it on 6 sides of the cavity that you're installing it in to ensure that you get that stagnant pocket of air that's happening in the spray foam automatically just by the nature of the material. So whenever the code is asking for a supplemental air barrier, it's primarily because it's assuming that you're using an air permeable material like cellulose or fiberglass or rock wool. If you're using a spray foam, you don't have to put that air barrier, that supplemental air barrier behind the tub on the exterior wall, for example. Does that make sense? Okay. So the whole idea of insulation in itself is that it's helping us gain control and predictability of the heat flow or heat transfer in the house across that building thermal envelope that we clearly defined. Energy always moves from higher concentrations, from warm to cold, from higher concentrations to lower concentrations across that building thermal envelope. And that temperature difference helps us understand that delta T. In this case, we have 68 degrees inside, 10 degrees outside. We have a delta T, or temperature difference, across the building thermal envelope of 58 degrees. So I know my heat drive is from inside to outside. So it's a heating dominated scenario here. We also have cooling dominated scenarios in the summertime where the heat drive is from one direction, is from the outside to the inside. Now, our building thermal envelope is our primary means of controlling the heat flow in or out of our houses there. And it also is used to define our design temperatures when we're designing a heating and cooling system. So the code tells us that we have to have a maximum of 72 degrees for heating and a minimum of 75 degrees for cooling. And then in our HVAC design, when we do our manual J to get our heating and cooling load for the house, the jurisdiction's telling us what's the worst case scenario for our wintertime design condition and our summertime design condition, so that we can, on the worst day of the year, determine what's the heat flow, what's the maximum number of BTUs that are leaving the house that I need to make up with my HVAC system on the cold day, and what are the maximum number of BTUs coming into the house that I need to cool off, in essence, in the summertime of the season there. So the direction of heat flow, the direction of energy, the direction of moisture, the direction of pressures is always from high to low, more to less, hot to cold, in essence. It's just a fundamental principle of building science. And you can use that fundamental principle to try and diagnose what might be going on in a particular situation in the house, either from a heat loss perspective, an air loss perspective, a moisture issue that's happening in the house. All of these things move from higher concentrations to lower concentrations until ultimately equilibrium works. Now, heat in itself moves by the process of conduction, convection, and radiant energy movement. Now, the code traditionally has only been concerned about conduction until about the 2012 International Energy Conservation Code, when blower door testing and air leakage became a mandatory requirement of the code. Now we understand that convection, the energy that's moving with air, is equally or more important than the energy that's conducting directly through the assemblies from hot to cold there. And then radiant energy is happening in our houses as well. You guys might have a lot of experience with it, with a radiant heating system there. This is just energy that's moving literally from through space or through air, well, basically through space, from hot to cold. The best example is from the sun to the earth. It's literally moving energy through space, from the sun, high energy source, to the earth, low energy source, where it's being absorbed there. The codes, we don't deal with it a lot now, but the code in the 2024 ICC, you start getting radiant barriers and reflective insulations being defined in the codes. We don't deal with it very often in our climate zone, but just so you know, it is now in the codes as well. All of these heat transfer mechanisms happen simultaneously, but understanding how they happen independently can help you, again, diagnose what might be going on with a building failure in a house that you have. When we talk about heat flow specifically, we're talking about reducing the heat flow with U factors and R values. And just to ensure we have a common understanding, R values are defining the resistance to the flow of energy of a specific component. So we can talk about the R value of a stud or the R value of a piece of insulation. But once you put the stud in place, the insulation in place, the exterior sheathing, the interior drywall, air films on each side, and your siding or cladding systems on that, we now have an assembly of things. Each of those components have an R value. And in order to talk about each of those components as a total assembly, we have to talk about U factors or U values. U factors describe the assembly, the resistance of the flow of energy through the entire assembly. R values talk about just through that specific component within the assembly. That's why we talk about the U factors of windows and not the R value of windows, because the windows are comprised of a number of layers of glass, the edge spacer, the hardware, the frames, all these different pieces of the assembly. And it just doesn't make sense to talk about each piece of the assembly. We just talk about the whole window unit as a U factor. Whereas we talk about the cavity insulation as R20 bad or R20 blown spray foam, for example. Now, the insulation itself, regardless of the insulation, it works exactly like it works in our clothing here. So this person's wearing a fleece jacket. The objective of the fleece jacket is to trap a pocket of air and keep that pocket of air stagnant against the body in order to resist the flow of energy. So the insulation traps a pocket of air, but we need that stagnant pocket of air. So what happens on a windy day when you go out skiing or running or biking or whatever, and it's windy and your fleece jacket, you're still cold because the fleece jacket isn't trapping that pocket of air. That's when we put on a nylon shell over the insulation in order to get the air barrier on top of the thermal barrier there. Now we have a system that works, and that system ultimately is working in the assembly. So the same thing is happening in our house, where we have either air permeable or permeable insulation installed in the assembly. We enclose it in the air barrier system there so that we can trap and keep that stagnant pocket of air, and we can make that insulation work and work properly there. So from a code inspection, what we're seeing now is that people are going in to inspect these houses, and they're no longer just going in and saying, yep, you got pink in the wall, and walking out. They're now looking at that assembly and saying, has it actually been installed to perform? Has it been installed to trap that pocket of air? What type of air barrier system is it going to be installed in? And are there gaps, voids, and compressions that change its R value from what you proposed to actually put in the house? Now, this insulation can only work in the cavity that has been installed in, and we have a significant amount of that assembly that is not covered by cavity insulation. So the R value of a stud is something like a 2x6 stud is something like R5.5 because the R value of wood is about 1 per inch. So we can improve the performance of our assemblies by adding continuous insulation in it. So I've got the benefit of increasing the surface temperature and reducing the possibility of condensation in my assembly, but I've also increased the R value of the total assembly. So when I say, and I'm a builder, and I say I build a 2x6 wall that's insulated with R20 blown fiberglass or R23 blown fiberglass, and I think I'm doing really well, the reality is when I do an area weighted average of a standard 16-inch on center framing package, that R23 for a whole wall R value, including the studs, comes out to be about R13. And then I add the windows to the equation, because my window has an R value of maybe 3 to 5 compared to my cavity that has a R value of 23, and I cut it in half again. So my whole wall R value is somewhere closer to 7 to 8 when I blow my 2x6 wall with R23 fiberglass insulation there. And it gets worse the bigger the window to wall ratio is, which takes us back to what we were talking about before, potentially putting a design constraint on the architect that says, I need you to justify every single window opening because it has such an impact on the performance, the comfort, and operational costs of this house. So justify that window, justify that window, that wall of windows. Do I need a wall of windows to maximize my views? Do I need a wall of windows to maximize my indoor-outdoor connection? Or can I have strategically placed windows and lower my overall window-to-wall ratio and get completely different level of performance and comfort for that occupant with the same connection to the outside, with the same optimization of the views to the outside there. So again, it's a team sport. Control and predictability. What am I trying to show here? So the insulation here is just giving us an idea of, this is just insulation in the wall cavity itself. This is just adding 1/2 inch of rigid foam to the outside. And you can see that I can no longer see each stud through there. So I've reduced the thermal break across that stud by doing that. And we are also, again, addressing condensation. So in this example, I've got a Pepsi that I took out of the cooler. I've got condensation, but I've taken a sip out of the Pepsi. What's happened to this side of the Pepsi can versus this side of the Pepsi can? And you can see this line of condensation.
It's warm.
In essence, I've warmed up this assembly, and therefore I'm not getting condensation anymore on that assembly. So this, in that previous example, this would be my 40-degree exterior sheathing. And if I added insulation to it, I would warm up that assembly. I would never be able to get that condensation on that surface again by adding that conditioned space. Okay, so to get control and predictability of air, we've talked about moisture flow, we've talked about thermal flow. Airflow, we're basically ensuring the continuity of our air barrier, and we're testing for it using a blower door test to test for that. Once we have that control, we also need to ensure that we have whole house controlled mechanical ventilation systems installed in our house. This is a code requirement. We did a residential energy field study across the state of Colorado, testing houses in almost every county across the state. And this code requirement for whole house controlled mechanical ventilation, in addition to spot ventilation around the house, only 50% of the jurisdictions we tested in were requiring or ensuring that whole house controlled mechanical ventilation was installed. What we're talking about is either supply, exhaust, or balanced ventilation strategies. In your climate zone, the code requires balanced ventilation strategies. So that leaves you only ERVs or HRVs, heat recovery ventilators or energy recovery ventilators. Everybody understand what those systems do and how they work? Because I don't have a specific slide on it. I can explain it if we want to.
Yeah, it'd be great if you could explain it
Okay.
so
So
briefly.
yeah, an ERV and an HRV work in the same way, but the old work in basically the same way. Ultimately, the idea is that we've built our house as tight as we possibly can to gain control and predictability of the house, of airflow, of moisture flow, and thermal flow in that house. the code is asking us now to introduce relatively fresh air, assuming the air outside is fresher than the air inside the house, so that we have fresher air for the occupants to breathe. But it also gives us background moisture control inside the house so that we don't get condensation on windows or other hard surfaces that are connected to the outside. In the code is asking us in your climate zone to use balanced ventilation strategies. So an ERV and an HRV fundamentally work in the same way. We have 4 ports on them. We're exhausting air from the inside, and it goes across a core to the outside. That air on the inside is carrying heat and moisture. Simultaneously, we have air coming from the outside and going to the inside, and it's crossing that same core. A heat recovery, the energy is moving in from the airstream that's exiting the house to the airstream that's entering the house. With an energy recovery ventilator or an ERV, moisture and heat are being transferred from the air that's leaving the house to the air that's going out of the house. Air always goes from moisture and energy always moves from higher concentrations to lower concentrations. So since in the wintertime, we have more moisture inside and more heat inside, that energy and moisture that's leaving the house is being transferred to the energy or to the airstream that's entering the house to bring more fresh air into the house and give us that, again, that more control of the moisture load inside that house. ERVs traditionally were thought that they only worked in moist, humid climates, but they work in moist, humid climates to keep the moisture out of the house. They work in dry climates to keep the moisture inside the house. Energy recovery ventilators only address the energy side of the equation, the heat side of the equation there. So the other thing with regards to balanced ventilation in your climate zone is it has to be at least 65% efficient at doing that energy and moisture transfer at 32 degrees. So you have to specify the correct assembly. It doesn't mean that you don't also have to do spot ventilation in that house. Spot ventilation is different. It's trying to get moisture loads up and out of the house as soon as they're being produced there, like in bathrooms, kitchens. We now have to test these systems, both spot ventilation in our kitchens, bathrooms, and laundries, and whole house controlled mechanical ventilation to make sure that they're pushing the required amount of air that's detailed out in the IRC. None of these installations will push 50 CFM of air because of the way that the duct was installed. All duct is required to be airtight. Not all duct is required to be insulated or inside the building envelope, but these types of installations just create too much static pressure that the fans can't overcome them to flow there. Okay, just a couple more things I wanted to talk about. We've talked about a lot of different concepts, and we've added a whole range of new vocabulary that you are now aware of. It's really important. Yeah.
We've got a question in the chat. Sorry, before you
Sure.
move on to her. Are you able to see it, or do you want me to read it?
Why don't you read it?
The question is, aren't ERVs and HRVs only required in climate zones 7 and 8 in the 2021 IECC? And Michael,
yes,
if you want
true.
to come on.
That's true. In the 2024, it moves down to climate zone 6. I'm sorry, I thought you had moved there.
Great, thank you for that.
Are you considering moving to the 2024?
At some point, yes. No, in the not too distant future.
Yeah, so beware. It's coming to your neighborhood. Okay, so again, back to vocabulary. Air barriers, vapor barriers, weather-resistant barriers. An example of 3 types of barriers that we're talking about. Air streams. We talk about infiltration and exfiltration with regards to blower doors, makeup air, fresh air, ventilation air, combustion air. All these different things that we're talking about. when you mix up or when you're talking to somebody, it becomes really important now to use the right language so that everyone has the same understanding about what you're talking about. If you're talking to me about whole house controlled mechanical ventilation and you're using the terms makeup air, I probably am going to misunderstand what you're talking about. So, another example is, like I said before, vapor retarders and vapor and air barriers. The gentleman asked the question about air barriers. I thought he was talking about vapor retarders, and that's why I stopped you in that, because I wasn't sure what you were talking about. So again, the other thing we need to understand is the difference between drying and breathing. Houses don't breathe. People breathe. Houses dry. We tend to use the connotation of this house is breathing for the house drying, but you might lose somebody that you're talking to when you're trying to explain what's going on in that house. And then again, I talked about vapor barriers, weather resistant barriers, and so forth and so on. There are a ton of resources out there where you can get more information. One of the big ones is the Building America Solution Center. This Solution Center has a couple of really cool tools, like a condensation calculator. You can build a simple assembly in here and get an idea what type of condensation potential or risk potential you might have, plus all these other things that are here. Buildingscience.com is another great resource. Green Building Advisor is another great resource. And there are other resources through Passive House Network, through 475 Air Barrier Association, and programs that are out there. So if you need resources, they're out there for you. Also, you can always contact me if you have questions as well. I wanted to ask real quick, because we are doing this in the context of code, what do people think minimum means in relationship to code? I'll tell you what I hear most often when I talk about minimum and code. Minimum allows us to build the shittiest legal house we're allowed to build. And I just bring that up because that maybe was true in the way distant past, but ever since at least the 2012, even the 2009 IECC, a code built house can be a really good built house, really well performing house. The reality is that minimum doesn't mean bad. We tend to put a bad connotation on it when we talk about it from a housing perspective there. The minimum is just means the smallest amount that's required. And on a national level, we created these groups that come together, this committee that comes together to develop a code, and they determine what's the minimum required that is easily achievable and cost effective for the average person in the United States to achieve. If it's installed properly and in accordance to the code, and it's enforced properly, you're going to get a well-performing house. You don't necessarily need to go, way beyond that there. What we see when codes get adopted, and this happened in the 2012 and the 2021 IECC, is that people start thinking about this apocalyptic thing happening, that it's just going to change the way we do things so much. And the reality is that it doesn't change. That change, and in terms of the way we build, it doesn't have to change. The way we execute things and our understanding of building science and incorporating it and applying it, that definitely changes. What ultimately really changes is the performance, the comfort that's gotten out of these houses. From the 2006 to the 2009, if things were built exactly the way that the code is asking it, we got about an 8% increase in efficiency in those cycles. That came on the back of increased requirements for R values and U values. To the 2012 IECC, we got almost a 19% increase in efficiency. That came on the back of now a mandatory requirement to blower door test your house and achieve at least a 3 air changes per hour requirement. So an understanding that convection is equally as important as conduction. That code change was so big that nothing happened in the 2015 and almost nothing happened in the 2018 IECC. In the 2021 IECC, the thing that changed was not the real base requirements. A little bit changed in R values, but the main thing that changed here was the adding of what's called additional energy efficiency requirements. The additional energy efficiency requirements are what gave us this basic almost 9% increase. So you have to meet the base code level, and now the code is asking us to do something more because the base code is all about the building thermal envelope. It doesn't care what efficiency furnace you put in or boiler you put in the house or water heater. That's now taken care of by these additional efficiency features, and you have a variety of choices that you can do. So there's lots of flexibility built in there. The 2024 that you might go to in the past just revamps the additional efficiency packages and gives you even more opportunities and more flexibility in that area there. So again, it comes down to the building thermal envelope and understanding the building thermal envelope. It comes down to the compliance path that you choose. And what I would ultimately say is that we're too fixated on the R value table. The R value table, this is from the 2024 IECC. You can see that the R value changed from the 2021 in your climate zone. It went from 60 back down to R49. So the R values are going to change a little bit from time to time there. This is what changed, specifically in climate zone 5. But when we fixate on the R value table, we forget that we lose flexibility, and we forget the kind of professionalism that our industry is all about, because the performance approaches, the approaches that use software, even the prescriptive software compliance approach, which is the res check software approach, allows us to do what's called a trade-off. A trade-off's goal is to keep a balanced energy budget. So the energy budget would be represented by the green ball here. You're allowed to do all kinds of things with the silver balls to create that balanced energy budget that the energy code is trying to do. And through using an energy model, you can try and fail a million times before you ever buy a nail to start building that house, to determine, first of all, how am I going to achieve code? Maybe second of all, how am I going to do that in the most cost-effective way? And third of all, how am I going to apply the building science that's wrapped into the code to create a structure that performs to the requirements of my client and ensure that I'm lowering my risk as a builder, and I'm going to make a structure that works and performs. So the performance approach is where we should be moving. It increases the professionalism of our industry. It gives you tons of tools to make it the most cost-effective product, and also to enhance your bottom line ultimately. The performance approach also helps us apply the building science in a little bit easier way. It gives us that control and predictability. We want to ensure that we have that drying potential. We have the synergy from applying that science, and that ultimately we have to use the right language so that everybody knows what we're talking about there. So if you want to learn more about building science in our industry, the Colorado Home Building Summit is happening again in Glenwood Springs on August 20th and 21st. Everybody's welcome to go. You can go to bsandbeerdenvermetro.info to find more about that. And if you have any other questions that might have come up through this, don't hesitate to reach out and we can get your questions answered. And also there's the code hotline that's available. I didn't put a link to that here, but Chad or Julie can get you a link to that. The code hotline will answer questions about any code that's being executed in the state. And those answers come out within 48 hours of your question. So thanks so much for your time.
Thank you, Robbie.
Thank you, Robbie. That was great.